Ever think about what happens when you open like an app on your phone or when a web page loads? It seems so simple, so instant, almost like magic.
Yeah, it is kind of magical, isn't it? But there's so much happening behind the scenes. This unbelievably complex web of systems all working together.
Right, like we see this polished, easy to use interface, but under the
It's
surface.
like that iceberg analogy, right? We see the tip, but underneath, it's massive and intricate, holding everything up. All that complexity is what makes our online experience so smooth.
Exactly. And today we're going deep into those hidden depths. It's like we're getting the blueprints to the digital world. We've got all these notes on how different systems are designed, stuff like the process of deploying code, those huge platforms behind Uber, stock trading, Twitch, even Amazon.
And we don't just want to describe these systems, we're going deeper. We're going to
Mm.
pull out the core principles, the fundamental considerations, like how do you build something that handles a massive amount of users and data but stays super reliable? It's about understanding the why, not just the what.
Okay, sounds good. So right off the bat, our notes emphasize this big difference between functional and non-functional requirements. It's not just about what the system does, but how well it does it.
Absolutely. So the functional requirements are like the basic things it needs to do. Let's take a stock trading platform. The core function is letting users trade, right?
Yeah.
That might involve a function called, say, place trade.
Right, where you put in the stock, the price, how many shares.
Exactly. And you see similar core functions everywhere. With Uber, it's requesting a ride, maybe a get drivers near me request. For Twitch, it's got to be streaming live video,
Mhm.
maybe with get live video.
Yeah. And think about online shopping. We all use that. Adding stuff to your cart. That's going to be something like an add to cart function.
Right. And these just the obvious ones. Even a simple to-do list has got to let you add and see your tasks. And then there's user authentication, logging in. Almost every system needs that.
Right, right. So we got the basics, but then you bring in these non-functional requirements. That's where quality and performance come in.
Yeah, like how reliable is this thing? For systems like stock trading or Amazon, any downtime could mean big money lost. And their reputation takes a hit too. They need to be up pretty much all the time.
And how do they measure that?
We see a lot of talk about nines,
Hmm.
like 99.99% uptime or even better. So 2 to 4 nines of availability are what they aim for.
Wow, that's got to take some serious infrastructure to pull that off. And then you've got latency, how fast the system responds.
Yeah, latency is huge. Think about high-frequency trading. Those guys need their orders processed instantly. Every millisecond counts.
Right, like the difference between making a profit or a loss could be that tiny bit of delay.
And for developers, they need to see their code changes go live quickly. That whole pipeline needs low latency.
Makes sense. What about scalability? How does a system handle a sudden surge in users?
That's where things get interesting. Imagine Uber on a Friday night. Huge spike in demand. Or let's say a code execution service gets slammed with a million requests every second.
Okay, yeah, that's a lot to deal with.
The system can't just fall apart. So you've got to design for that kind of scale from the beginning. Defining these non-functional requirements is critical. It's the foundation for any successful design.
So we know what the system needs to do and how well it needs to do it. Next, we need to figure out the volume. How much can this thing handle? This is where capacity estimation comes in, right?
Uh-huh.
And figuring out potential bottlenecks.
Exactly. We got to think about how many users we expect, how much data the system will handle, and the rate of incoming requests.
And you need to have some ballpark figures before you even start picking technologies, right?
Absolutely. And our notes have some crazy examples, like that code runner expecting 1 million requests per second, Uber potentially dealing with 10 million riders at the same time, or a stock exchange processing 1 million trades in a single day.
Whoa, those are some seriously big numbers. But how do these projections actually affect the system's design?
Well, they help us identify potential bottlenecks. Like if we're expecting a huge data set, we might need to think about splitting it up.
Like dividing a giant phone book into smaller regional ones.
Exactly. It's called partitioning or sharding. Spread that data across multiple servers to handle the load.
Got it. Distribute the load. And when it comes to all those requests coming in, how does knowing the expected rate help?
It lets us plan how many servers we need and design a good load balancing strategy. Our notes also talk about the Pareto principle.
The 80-20 rule, right. A small part often drives the majority of the results.
Right. In this case, it means a small portion of the data gets accessed way more often. So we can focus our caching mechanisms on that hot data.
So you're essentially giving priority to the stuff people need most often. That makes things faster.
Yeah, it improves performance and reduces load, but it's not a one-time thing. You got to keep monitoring because what's hot can change over time.
That's a good point. It's not static. Okay, so we have all these components in the system. How do they talk to each other? That's where API design comes in, right?
Absolutely. API stands for Application Programming Interface. It's basically a set of rules that defines how different parts of the system can interact. It's like a common language for them.
So it's how they exchange information.
Exactly.
Yeah.
And our notes give us some specific examples. Remember that place trade function for stock trading, or get drivers near me for Uber, and then there's get live video for Twitch, add to cart for Amazon.
So these are all ways for one part of the system to like request something from another part.
Yeah, exactly. And designing these APIs well is super important. They should be easy to use, consistent, and secure because you don't want any unauthorized access.
Right, makes sense. So the system knows what to do, how much it can handle, how to communicate internally. Now, where do we put all this data? That brings us to database choices, right? The schema.
Yeah.
This feels like a really big decision.
It definitely is. Choosing the right database depends on the kind of data you have and how you're going to use it. Our notes talk about a whole bunch of different database types. Each one has its own pros and cons.
Okay, let's break it down. First up, we've got the classic SQL databases, like MySQL or PostgreSQL.
Right. They're like the workhorses for relational data. SQL databases are great for structured data, where the relationships between different pieces of information are important.
So if you need to keep track of connections between different data points.
Exactly. They also provide what we call ACD properties:
Which stands for?
atomicity, consistency, isolation, and durability. They basically guarantee that data is processed reliably. Super important when you can't have any errors, like with financial transactions.
Yeah, you definitely don't want any mistakes when dealing with money.
Right. So in systems like stock trading platforms, or for uploading file chunks securely like Dropbox does, SQL is a good choice.
They're really reliable, but what are some of their limitations?
Well, they can be a bit slow when you have a massive amount of write operations. And their replication usually relies on a single leader node.
So they're better for systems that mostly read data.
Generally, yes. Then we get into the world of NoSQL databases. They offer different approaches.
Like Cassandra, I see that one mentioned quite a bit.
Cassandra is designed for speed and high availability. It can handle a ton of write operations really fast, and it does this through a leaderless replication model.
Leaderless. How does that work?
Instead of having one main server, multiple nodes can accept writes at the same time. Then the system eventually reaches a consistent state. It's called eventual consistency.
So there might be a slight delay before all the copies of the data are exactly the same.
Right. That's why it's great for applications that prioritize speed and can tolerate a little bit of inconsistency. Like, think about Twitter's real-time feed or chat apps like WhatsApp.
But then what happens if two nodes have conflicting information?
Usually it's last write wins. The most recent change gets priority.
Interesting. Okay, what about MongoDB? It's another NoSQL database, right?
Yeah, MongoDB stores data in flexible documents. It's a good mix of structure and adaptability. Think of it like JSON-like documents.
So it's kind of in between SQL and the more free-form NoSQL databases.
Yeah, and our notes mentioned it's been used by services like Pastebin.
Okay, makes sense. Then we have these key value stores like Redis and Memcache. These are all about speed, right?
Yeah, they're incredibly fast because they keep everything in memory. So both reads and writes are super quick. They're great for caching frequently used data.
Like we talked about with rate limiting and browser caching.
Exactly. Plus, Redis has some cool extra features like geospatial indexing, which is useful for location-based services, like how Lyft figures out where drivers are.
Ah, that makes sense. But if everything is stored in memory, there must be a limit to how much data they can handle, right?
Yeah, you hit the nail on the head. They're not good for huge data sets, and their querying capabilities are a bit limited too.
Okay, so they're good for specific tasks where speed is crucial. What about graph databases? They sound like they're built for a very particular kind of data.
They are. Graph databases, like Neo4j, are specifically designed to handle relationships between data points. Think social networks.
Right, where connections between people are the most important thing.
Exactly. So if your application is all about understanding those connections, a graph database might be a good fit.
Then we have time series databases like InfluxDB and TimescaleDB.
These are great for data that's tied to specific points in time, like system logs, metrics, sensor readings, things like that.
So basically anything where you need to track changes over time.
Exactly. And they let you query that data efficiently. Really helpful for stuff like distributed logging, where you need to analyze trends.
Wow, it's amazing how each database has its own specialty. It really shows that picking the right one is about knowing what your system needs.
Absolutely. Understanding those functional and non-functional requirements is key. You need to consider things like data consistency, read-write patterns, and how scalable the database is.
So now we know where the data lives. Let's talk about how to make sure the system runs smoothly and can handle problems. Our notes have a bunch of different architectural design patterns. Seems like load balancers are pretty important.
They're essential, especially for large-scale systems. They're like traffic cops. They distribute incoming requests across multiple servers, making sure no single server gets overloaded.
So they help keep the system up and running even if one server goes down.
Exactly. They improve both availability and responsiveness. We see mentions of active-active and active-passive configurations.
And what's the difference?
Well, in active-active, all the servers are handling requests. In active-passive, you have some servers standing by, ready to take over if an active one fails.
So it's all about redundancy, like having backups ready to go.
Right. And these load balancers are super important for sites like Uber and Amazon that get a ton of traffic.
Makes sense. And then there's caching. We already talked about it a bit, but where else does it come into play?
Caching is like a secret weapon for making systems run faster. It's all about storing frequently accessed data in a place where you can get to it really quickly.
So like instead of having to fetch the same data from the database every time, you have a copy ready to go.
Exactly. Your browser does this all the time with web pages. It stores static elements like images or code so it doesn't have to download them again on every visit.
Right, so that's why sometimes when you go back to a web page, it loads super fast.
Exactly. And then you've got CDNs, content delivery networks. They take this concept to the next level.
How so?
CDNs cache content on servers all around the world. So when you request something, you get it from the server closest to you. That makes things way faster for users.
Well, that's cool. So it's like having a local copy of the website already there.
Right. And then there are in-memory caches like Redis and Memcache that we talked about earlier. They're used within the application itself for super fast data access.
Okay, lots of different types of caching going on. What about message queues, like Kafka and RabbitMQ? They seem important for letting different parts of the system work independently.
They're crucial for that. They allow asynchronous communication. So one service can send a message to another without having to wait for a response.
So it's like sending a letter instead of having a live phone call.
That's a good analogy. It makes the system more resilient and scalable because services aren't directly dependent on each other.
Okay, so what are the differences between Kafka and RabbitMQ?
Kafka is built for high throughput, ordered streams of data. Think about things like tracking changes in a database or managing the sequence of video segments in a streaming platform.
So things that need to happen in a specific order?
Exactly. And it's also very durable. It makes sure messages aren't lost. While RabbitMQ is often used for faster in-memory message delivery, it's really good for tasks like triggering video processing or sending notifications.
Got it. So Kafka is more about reliable ordered streams. RabbitMQ is more about speed.
That's a good way to put it. And if you're already using Kafka for data streams, our notes mention stream processing frameworks like Flink.
What are those for?
Flink lets you process data in real time as it comes in from Kafka. So you can do things like update Twitter timelines or update data in Cassandra based on events happening in the stream.
So you're analyzing and reacting to data on the fly. Sounds powerful.
It is. Now, what about those applications that need real-time two-way communication, like Twitch chat? Our notes talk about server-send events and WebSockets.
Okay, yeah. So what are the differences between those two?
Both of them are used for real-time interactions, but server-sent events, or SSE, are unidirectional. It's just the server sending data to the client.
Like a one-way street.
Right. And it automatically tries to reconnect if the connection drops. Apparently, WhatsApp looked into using SSE or something called long polling.
Interesting. So what about WebSockets?
WebSockets are bidirectional, so both the client and server can send data back and forth.
So it's like a two-way conversation.
Yeah, but they don't automatically reconnect if the connection's lost. And they can have this problem called the thundering herd.
What's that?
It's when the connection drops, and then all the clients try to reconnect at the same time. It can overwhelm the server. Imagine everyone trying to get back into a stadium through one single door.
Ah, that makes sense. Okay, what else do we have? Search engines, Elasticsearch, and Lucene. Those are essential for any application that deals with large amounts of data, right?
Absolutely. Think of Twitter search or looking through tons of video metadata. They're designed to index and search massive amounts of data efficiently, much more powerful than what regular databases can do.
So they're the go-to for finding specific information in a sea of data.
Exactly. And then you've got blob storage solutions like S3 and GC storage. They're used for storing large files.
Like images and videos.
Yeah, those are good examples. They're designed to be super scalable and cost effective.
So if you need to store a ton of big files, that's the way to go.
Right. Now, remember we talked about Uber earlier? Well, they also use DNS and path-based load balancing.
Okay, can you remind me what those are?
So DNS load balancing uses the domain name system to send requests to different servers based on the user's location. It tries to find the closest server.
So that helps reduce latency for users all over the world.
Exactly. Path-based load balancing is a bit different. It sends requests to different servers based on the URL.
So you can send API requests to one set of servers and website requests to another.
Precisely. It gives you more control over how traffic is distributed.
Got it. And finally, there's rate limiting.
Right. Rate limiting is all about preventing abuse and making sure everyone gets a fair share of the system's resources.
So you limit how many requests a user can make in a certain amount of time.
Exactly. We see two main strategies: fixed window and rolling window. Fixed window resets the counter at specific intervals. Rolling window looks at a sliding time window.
That's a lot to take in. So many different patterns and techniques to consider. It seems like picking the right combination is key.
You got it. Each pattern solves a specific problem. It's about understanding what your system needs and then choosing the tools that fit.
All right, we covered a ton of architectural patterns. Now let's dive into some of the fundamental system design concepts that make these patterns work. Consistent hashing, for instance.
Consistent hashing. It's a clever way to distribute data across multiple servers. What makes it special is that it minimizes data movement when you add or remove servers.
Okay, I'm not sure I follow.
So imagine a circle with your servers placed around it. Data items are assigned to the nearest server on the circle, going clockwise. When you add or remove a server, only the data near that change needs to be moved.
That's much better than having to rearrange everything.
Exactly. It helps keep things running smoothly in a system that's constantly changing.
Got it. What about leader election? Our notes
Mhm.
mentioned using Zookeeper for that.
Right. In distributed systems, you often have multiple nodes that can do the same job. Leader election is how you choose one to be the boss, the coordinator.
So, like, if one server fails, another one can step up and take over?
That's the idea. And Zookeepers is a service that helps manage this process. It makes sure there's always a leader and handles the transition smoothly.
So it keeps things organized.
Exactly. And our notes mention it being used for managing databases in Pastebin and coordinating those worker nodes in job schedulers. Then there's sharding or partitioning, which we've touched upon a few times.
Right, that's about splitting data across multiple servers,
Yeah,
right?
it's all about handling massive data sets and high traffic.
Yeah.
You basically divide the data or the workload so that one server doesn't have to do everything.
So it's another way to scale horizontally.
Exactly. Like starting by user ID in HBase or by chat ID in Cassandra.
And then there's replication, which is about having backups of your data, right?
Right. Replication is all about keeping the data safe and ensuring the system keeps working even if one server goes down.
So you have copies of the data on multiple servers.
Exactly. And there are different ways to do it. Single leader replication, like in SQL and MongoDB, where one server is the main source. And then there's leaderless replication in Cassandra, where multiple nodes can accept writes.
Right. We talked about that earlier. So it's about choosing the right replication strategy based on your needs for consistency and availability.
Precisely. Now, for systems dealing with financial transactions, ACD transactions are crucial.
To ensure that money is being moved around correctly.
Exactly. ACD stands for atomicity, consistency, isolation, and durability. These properties make sure that even if there are errors or multiple operations happening at the same time, everything is processed reliably.
So no money disappears or gets duplicated accidentally.
Right. Super important for keeping accurate financial records.
What about heartbeats and fencing tokens?
Those are ways to make sure distributed systems stay healthy and things happen in the right order.
Okay, can you explain that a little more?
Sure. Heartbeats are basically signals that a service sends out to say, hey, I'm still alive. If a server stops sending heartbeats, it means something's wrong.
So it's like a health check.
Exactly. Fencing tokens are a bit more complex. They're used to make sure that operations on shared data happen in the correct order.
So if multiple clients are trying to update the same data at the same time?
Exactly. Fencing tokens help prevent conflicts and ensure consistency.
Got it. Makes sense. What about idempotency?
Idempotency means you can perform an operation multiple times without causing unintended side effects.
So if you accidentally run the same command twice, it doesn't mess things up.
Right. Like depositing money into an account. Doing it twice shouldn't add the money twice. It should only happen once.
Ah, that's a good example.
And then you have the pub-sub pattern.
Which is short for?
Publish subscribe. It's a way for different parts of the system to communicate without needing to know about each other directly.
So one part can publish a message, and anyone who's interested can subscribe to receive it.
Exactly. Like if a trade is executed, you can notify all interested parties without knowing specifically who they are. And of course, CDNs are another important concept for distributing content globally and making sure users have a fast experience.
Yeah, we talked about them earlier. They're like having local copies of websites all over the world. Amazing how all these different concepts come together to make complex applications work. Now, our notes also touch upon some design considerations that are specific to different types of applications.
Right, like the fundamental principles are the same, but the priorities and challenges can be quite different depending on what the application actually does.
Makes sense. Let's go through some examples.
Okay, so for something like a code deployment system, you need really seamless integration with Git, those version control systems developers use.
So the process of pushing code changes and getting it live needs to be smooth.
Exactly. You also need good build and test pipelines to make sure the code is working correctly. And you need ways to manage different environments like staging and production.
Right, different versions of the application for testing and for live users.
Exactly. And then there's job scheduling, handling potential failures. It can get quite complex.
Lots to think about.
Yeah. Now think about a ride-sharing platform like Uber. Their big challenges are accurate location tracking in real time.
Right, you need to know where the drivers and riders are at all times.
Exactly. Then they need to match drivers and riders efficiently. And of course, payments need to be processed securely and reliably.
And then there are the different service tiers like UberX, Uber Black, and so on.
Right, lots of moving parts there. Now, if we shift to stock trading, things get even more intense.
How so?
Well, you need to handle different types of orders, limit orders, market orders, and so on.
So different ways to buy and sell stocks.
Exactly. Then there's the whole settlement process, which is how trades are finalized. And of course, there are strict regulations to comply with.
Right, the financial world is heavily regulated.
Absolutely. And the system has to stay stable even when the market is going crazy.
Yeah, can't have the system crashing during a market crash.
Exactly. Now, live streaming platforms like Twitch are all about handling massive amounts of video data.
Yeah, sending video to thousands or even millions of viewers simultaneously. That's got to be a challenge.
It is. They need low latency streaming so there's no lag. And then there's real-time chat.
Which needs to be fast and synchronized for everyone.
Right. Plus, they have to manage subscriptions, moderation.
Mhm.
It's a whole ecosystem.
And then we have e-commerce giants like Amazon. Their systems are mind-bogglingly complex.
They are. Just think about the scale of their product catalog. It's constantly changing. And they need a really good search engine so users can find what they're looking for.
Right. And then you've got the whole shopping cart, order processing, shipping, and logistics.
Yeah, they're basically running a global supply chain alongside their online store.
It's a lot to manage.
And then, don't forget personalized recommendations. That's a big part of their success.
So even seemingly simple applications like Paste-to-Bin or those URL shorteners like TinyURL have their own challenges, right?
Absolutely. For them, it's all about generating and resolving those short URLs efficiently. They have to handle potential collisions.
Collision.
Yeah, when two different pieces of content accidentally end up with the same short URL.
Ah, that would be a problem.
Right. And they often pre-compute keys to make things faster.
To speed up the process of generating those short URLs. Makes sense.
Then you have social media platforms like Twitter. They're dealing with huge amounts of user-generated content.
Yeah, millions of tweets every day.
Exactly. They need efficient ways to handle follower relationships, identify trending topics, make search work well, and they have to make sure the user experience is consistent, even though the data might not be perfectly synchronized across all their servers.
Right, because of that eventual consistency we talked about earlier.
Exactly. What about file storage and sharing services like Dropbox? They're all about managing files and making sure they're accessible from different devices.
Yeah, that sounds complex.
It is. They have to handle uploads and downloads efficiently. Make sure file sharing is secure. They need version control so you can go back to previous versions of a file. And they need to keep everything in sync across your computers and phone.
A lot of behind-the-scenes work to make it seem so simple.
Right. And messaging apps like WhatsApp. They focus on real-time message delivery, sharing media, sending notifications.
Got to keep those notifications coming through.
Yeah, reliably. And video sharing platforms like YouTube, they have to manage video uploads, encoding and transcoding, streaming at scale, search, recommendations.
Seems like they're dealing with even more data than Twitch.
Probably.
Uh-huh.
And then there are those background services like job schedulers. They might not be flashy, but they're super important.
What do they do?
They manage tasks that need to run at certain times or intervals. And for them, correctness is more important than speed.
So they have to make sure those tasks are completed correctly, even if it takes a little longer.
Right. They also need robust error handling and monitoring to make sure they keep running smoothly.
Got it. So we've got job schedulers working behind the scenes, and then you mentioned distributed logging systems.
Yeah, they use those special time series databases to store and analyze log data,
Hmm.
essential for understanding how the system is behaving and troubleshooting problems.
So those databases are specifically designed for that kind of data.
Right. And then you have recommendation engines. They use machine learning and algorithms to personalize the user experience. Think about those. You might also like suggestions on Amazon.
Right. Or movie recommendations on Netflix.
Exactly. And then you've got notification services. They handle user subscriptions and send out those alerts through different channels like email, SMS, push notifications.
So many different ways to get notified these days.
Right. And sometimes you need something called a distributed lock. It's a way to make sure only one part of the system can access a shared resource at a time.
So it prevents conflicts.
Exactly. Even counting unique active users can be tricky at scale. They use special algorithms for that.
Seems like even simple tasks can get complicated when you're dealing with huge numbers.
They do. And finally, you have these distributed message brokers. They're used for reliable and scalable communication between different parts of the system. They often use long polling to keep the connection open and reduce latency.
Wow, we've covered a lot of ground here. So many different applications, each with its own unique challenges.
And yet it's amazing how many of the same principles apply across all these different systems.
So if we had to sum it all up, what's the key takeaway here?
I'd say the big lesson is that designing systems that can handle real-world demands is a multifaceted challenge. You need to really understand the requirements, choose the right architectural patterns, pick the right database, and use all these supporting technologies and concepts in a smart way.
And there's no one-size-fits-all solution, right?
Exactly. The best design depends on the specific application you're building, and you always have to balance trade-offs, data consistency, availability, performance.
It's about making the right choices for your specific needs. Well, this has been a really eye-opening deep dive. I feel like I have a much better understanding of how the digital world works now. And for you, the listener, I want you to think about an app you use regularly, maybe your favorite social media platform or that online store you always shop at. Can you imagine what kind of system design principles are at play behind the scenes? What kind of trade-offs do you think they had to make? It's pretty fascinating to think about.
It is, and remember, the world of system design is always evolving. There are always new challenges and new solutions being developed. It's a dynamic field with lots to explore.